find out the result of these 3 different circuits. Do you have questions? Nothing? Is it clear for everyone?
For me, it takes some time to find them, but it's clear.
Okay. Again, as you can, we will move through these exercises at the very beginning. Of course, it's gonna take you maybe, I don't know, like 15 minutes. But the day of the exam, this should, well, applying mesh law and node law should only take you like a few minutes. But after some training, you will get used to this. No questions? Can we move to the next exercise, or do you want me to step back on some concepts or circuits?
For me, it's fine.
Okay, no more questions. Okay, so let's move to exercise number 5, which gonna be super quick because it's super easy. In front of you, you have some graph presenting the characteristic function of a voltage generator. This is a non-ideal generator, because remember from the class, from the lecture, you learned that a voltage generator is delivering normally a fixed voltage, whatever the current is in the branch. So when you plug a voltage generator to whatever circuit, in fact, this voltage generator delivers always the same voltage, and it's adapting the intensity, the current, flowing through this branch, so this voltage is fixed. This is what we call the ideal case, but in the non-ideal case, in fact, this is a wrong way to represent a voltage generator. In fact, you have to associate a voltage generator with what we call an internal resistor, and then you have the rest of the circuit. But this is now your non-ideal generator. So if now you introduce a current, you said that this voltage generator is having some electromotive force E and a resistor, internal resistor small r, then using the receptor convention, you have something like this. So the full UG equals to E minus R times I. So you're not anymore in this case, but now you are facing this. Of course, the slope here is a bit exaggerated, but this is a concept. And this is what you have in front of you. So from the curve of the exercise, you can find easily this parameter and also this parameter. So E, you get it because when I equals to 0, then UG0 equals to E. So this is where the curve is cutting the axis here. And then you do a quick point, whatever specific point you find on your curve, and then you get the value of R, okay? So please go through this graph quickly and get me the value of E and R, please. Be really careful. The main mistake you can make on this graph is to forget the units. So on the x-axis you are in milliamp, not in amp, which means 10 power minus 3 amp. That's why you end up with here a power 3. Okay, so the 6 volt for E is pretty easy to catch. In fact, you just have to draw kind of a fitting curve on your graph, and you will see that it's crossing the y-axis at 6, and then you just pick like a point which is quite easy to obtain, which is the one at 3 milliamp equals to 3 volts. And you just have to write down this. So you have 3 volt equals to 6 minus R times 3 milliamp, and you end up with this small R. Okay?
If we don't have exactly 6 volt, does it matter?
No,
If
no,
I have to
no.
follow the black line and I have 5.6 or something like this.
Yeah,
5.8, I think.
it's fine. It's fine. It's just the concept. I want you to catch the concept. If the value is changing a little, it's fine. So now you know what the result will look like. So you're able to actually go through the rest of the exercise on your own. So this was the first question. Then second question, the difference is now you plug your non-ideal generator to another resistor. but at the end it's not changing the concept. UAB is corresponding to this UG we just drew, which means E minus RGI, which is also equals to R, which can vary, time I. So nothing new. This is just another experiment that you will be using such kind of setup during the lab for electrokinetics part 1. Maybe you already start this this lab.
No, we haven't. We
Okay.
finished optics and we haven't started.
Okay, so you will see such kind of setup, and this is a way, by playing with this setup, this is a way to get the value of the internal resistor. And we will discuss this during the lab with your professor, but if it's not clear during the lab why or how using this setup we can get the internal resistor, the value of the internal resistor, then we will discuss this during class.
So I don't exactly understand the equation we just did, because you have UG, so it's the tension.
You have this with here being R var, here being A, B. So UAB is like this. You have the current I flowing like this, which means that now if you, so this is E. So
Okay, I thought we answered the question, because in the question it's not written as a function of of I. It's just as a function of the other ones.
Yeah,
Okay.
of course.
So I didn't understand. Sorry.
No problem.
But can you keep explaining? Because I was.
Yeah, sure. So this is the full setup. Okay. I just label the various voltages. So this is U or G. This is U or var. And this is UAB. And remember that just previously we were saying that this UG was equals to this. But UG equals to UAB equals also to U or var, right? Because they are both considering these two nodes A and B. That's why I wrote here the final answers. This is straightforward.
Oh, but between UG and E, it's a minus or an equal sign?
Oh, sorry. Yeah, no, it's an equal. Sorry.
Oh, okay, I was confused.
Yeah,
Thank you.
okay. So now you move to the next graph, which is again the same questions. We ask you, what about the characteristic of a voltage generator? The only right answer is, of course, figure 3. And then you can move and get from the curve of figure 3 the typical parameters of your voltage generator, which are the E and the RG value. So this exercise, the aim, the goal of this exercise was just to introduce you to a specific characteristic of a non-ideal generator, which is going to be the case of what you encounter during the lab session.
Could you just explain? Yeah, I mean, I know it's just using the graph, but because I think I'm getting the wrong answers for R, because do we have to do something to convert it into ohms?
Yeah, again, you have the same problem since your current on the x-axis is in milliamp. It's not amp. To get ohm, you need volts and amp, but here you have volts and milliamp. So you have a 10 minus 3 factor.
Yeah, okay.
Okay. So remember just this type of circuit here that you will learn how to plug it during the lab, and during the lab session you will see what we call an impedance matching. I think we will do maybe this exercise a bit later, but this is the impedance matching type of circuits. Why? Because in fact the idea behind this circuit is to get the, here you have a resistor that you can move, that you can pick, that you can change, and the idea here is to have through this resistor the maximum of power. It's like, let's say you use an electric guitar and you plug it to an amplifier, but you need to, if you want the sound to be in the best condition, the maximum amplification, you need to adapt, in fact, your amp with your guitar. And your electric guitar has a specific internal resistor, and the same for the amp. So the idea here, and this is what we're going to do later and also in the lab, is to see how I can choose this resistor here, which can vary it to get the best power out of my amp. Okay, but we will see this later. Is there any question on this drawing, characteristics, parameters? Nothing? So now we are going to move to the rest of our exercise. From now, you know, as I said, almost everything you need for this class. The other things we are going to learn is to use some theorems. Superposition, Thevenin, Norton, Millman, and simplification theorems. But all these theorems are more or less a quickest way, or I would say another way to use Kirchhoff law, which is mesh and node laws. So the next exercise is a circuit that we're going to solve using these different methods. We're going to start with Kirchhoff law, and this is going to be the longest and more the method which is going to be the more complex And then we're going to see the others little by little. So let's start with these circuits. Here we go. E. And after the end of this exercise, you will realize that in fact, Kirchhoff law is really annoying and really complex for you because you get confused because you have a lot of equations that you have to solve. And for the rest, maybe of the exercises and even in the exam, maybe this is not the right way of doing it. The only thing is if you are completely lost, if you are completely lost and well, you don't see a thing or you don't know what to do, if you go through Kirchhoff law, you always go to the right solution. You end up with the right result anyway. So this is our circuit, R1, to R1, to R1, and R. The question is, what is the value here of the currents flowing through the resistor R between the node A and B? We are going to apply, as usual, the same protocol, which is labeling the currents flowing into every branch of the circuit, then labeling correctly the voltage between every dipole, which are every resistors here, and then so when you spread the currents, you're going to apply the node law each time you enter in a node, and then you're going to apply some mesh law, and you're going to apply the right amount of mesh law corresponding to the right amount of unknown you have. So you already have one unknown, but once you're going to start spreading the current through the circuit, then you will introduce other unknown. Okay, so let's just keep finishing here labeling. So here you have I0 because here you have a current generator which is delivering I0 current through the branch. So you can deduce here the current entering in R1. I will let you do this, and then of course you have another current I here in this branch in the opposite direction than I because of the node law I applied here in C. Then you apply the node law in D. So you are gonna introduce at least another current, which is gonna be another unknown. So you have two unknowns. So you need to apply two mesh laws in two different meshes. Remember, one really important thing is do not, it's an advice you can, but do not apply a mesh law in a mesh including a current generator. Because you don't know the voltage in between the terminal of your current generator. So by applying a mesh law in a mesh including a current generator, in fact, you're adding another unknown, which is the voltage in between the terminal of your generator. So here you have I0, which is the voltage between the terminal of the generator, and this is an unknown. Okay, so this is a bit useless to add another mesh with this current generator because you had another. All right, so I will let you go through this exercise. Keep spreading the current, keep labeling everything, apply twice the mesh law, and please give me the final result of the current. Hi. If you have questions, of course, or if you want me to re-explain, detail something. You can just write down the final answer you should end up with. So today it might take you maybe 15 minutes to get this result, but you should divide this time by 3 for the day of the exam. Again, by practicing and doing circuits again and again. And as I said, this is going to be the one of the more complex and longest method we're using, because we are spending a lot of times to spread and create the equation and solve the system of equation. But then you're going to see that we will use other theorem. They're going to ease our life, and we can move quicker to the final result. Do you see my mouse now moving on the screen or not?
No.
Oh, come on. And if I'm in like this, do you see a pen?
Yes.
Yes.
Okay. So maybe this is how I'm gonna do things. Please let me know if some of you already have the result. So I can just have an idea of your speed. Because maybe again, what is blocking you right now is math.
I have a question.
Yeah.
Between B and C, is it
Sorry, I
going to...
can't hear you well. Sorry.
Can you hear me?
Yeah, it's better.
Okay.
Thank you.
Between B and C, can we put the current in the other direction, or is it wrong?
Yeah, no. Again, it's up to you. Of course,
Okay.
you can label it in the other way. So the value of this current is going to change, and maybe you're going to label the voltage in between the terminal of R1 in the other direction also.
Yes. Okay. Thank you.
Yeah, but it's going to give you the same result.
Yeah. Thanks.
Okay. So just to help you, I write the two equation I get from the two mesh law I got, just to show you again that it's convention. I picked a different direction when I applied the mesh law in the mesh 1 and the mesh 2. Then here in this case, in fact, the two unknowns are still the current I, what we are looking at, and the other unknown is I1. I0 is known because this is the current delivered by the current generator, and the other voltage E is also known. All the value of the resistors are known. So you end up with these two equation there, and from here you have a system of two equations with two unknown that, and you can solve this, of course, quite easily to find the result. Do you have the concept of this, or do you have questions regarding the sign, the application of the mesh law, I don't know, anything? Were you able to find at the end the result?
No.
Is it because of math computation problem or of like?
I don't know.
Okay.
Because for the second equation, I didn't take the same positive.
Okay.
Yes, so I don't
That's
get the
fine.
same.
Well,
Yes, but then.
so you should end up with a minus sign in front of everything if you pick the same. Let's see if it's working here. So you see my pointer?
I don't know.
Yeah.
Yes.
Okay. So in this mesh, I use this direction, correct? And I can use the same direction in this second number 2 mesh, going from left to right. But if you do this, you will face every time all the voltage in the opposite direction. So you should end up with a minus in front of everything, which in fact correspond to a plus also because the equation equals to 0. So you should end up with the same equation than me. If you use the same label, of course.
Yes, I'll try.
Okay. So again, I think it's practicing, and what I realize is more that in physics, you have more issues with math rather than with the physical understanding of the concept of circuits and electrokinetics. So please practice your math, practice the solving of equation with unknowns, try to keep your training on so you will improve your speed of solving and computation.
I found a result.
Okay, cool. So please keep practicing this. Now I'm gonna start introducing the other method we're gonna use, or you may use, when you're gonna face different circuits. So we will start with the superposition theorem. Do you have any question before that I move to the next theorem on the concept? Now you should be just doing computation and math to get the final results. But if you have any question, issues on the physics, please let me know now before I move. So it's a no, and we move to the next. So be really careful now, because I'm gonna teach you another theorem, and you will go through it in the next part. Just I was looking at the time, and also just want to see if we have time to make more than one method. Maybe not, maybe we'll see. Okay, let's see. So let's start with superposition theorem. So the idea behind this theorem is that when you are in front of a circuit with multiple sources, then you can divide your problem by considering the contribution only of one source at a time. Just let's go back to whatever. Let me draw you a random circuit, just for you to understand the concept. Here we go. So I have here a circuit with 3 different sources. And let's say that I am interested in the currents flowing in this branch. I'm going to call I star. The idea behind this theorem is that I can try to find the contribution of only one source at a time, which gonna be how I'm going to use this. First thing is you let one source on and turn others off. What does it mean? When you turn a voltage generator off, so this is on, when it's off. In fact, a mnemotechnic way of remembering how it works is like erasing the cycle. So if you erase the cycle on the voltage generator symbol, then you end up with a wire. So it means that when you turn off a voltage generator, it's equivalent of having only a single wire between your 2 points. Okay? A and B. So now if I want to turn on this time a current generator, if you write this is a current generator on, and when it's off, you end up with something like this, which means, so this is what we call a closed switch, or a single wire. And this is an open switch. So an open circuit. Okay. This is really important to remember, this equivalence of current and voltage generators when you are in front of a circuit, especially because, again, you're going to apply this during your lab session. And when we ask you to turn off a voltage generator, it's not just take the switch of your voltage generator and turn it off. No, you have to take out the 2 wires going out from your voltage generator and link them together to make a single wire. Okay? So now, since you have this in mind, let's see how I'm going to apply the superposition theorem in such kind of circuits. So as I say, I let only one source on at a time. So let's see that now here, first option, second, I'm just going to leave the source I1 on and the others are going to be off. So I'm just redrawing the circuits in this case, and I end up with this. Okay? And I'm still interested in the current flowing here, which is not really I star, but in fact, I'm gonna call this I star, but only the contribution of E1. So what is I star E1 in this case? I have to go and calculate it. As soon as I get it, then I move to the next source. Let's say that now I'm just turning on the current generator, leave this on, and I end up with this. Still interested in this current that I'm gonna call I stars, and this time it's E0. Oh man. Move. Come on, why? Sorry. Here we go. So I start R0, then last circuit is leaving the last source on. So you are facing this circuit, still interested in this I star, now E3. So the idea here, because of the superposition theorem, instead of having to calculate the current into a more complex circuit, then you have to face different single mesh circuit. And at the very end, the important point is that in fact the I stars you're looking at is just sum of the various I star from all the contribution I1 plus I stars coming from the contribution of I0 plus I stars coming from the contribution of E3. Okay? You get that? This is the concept of what we call the superposition theorem. We add the contribution of every sources. So you let one source on at a time, you turn all other off, and then you do this for each source.
I have a question.
Yes.
Can we also let multiple sources on, for example, mix number 2 and number 4?
No.
Because it's in the same mesh.
No.
Okay.
No, it's one source on at a time because you're looking only at the contribution of one single source at a time. But then once you're going to redraw your circuits with only one source on, then you're allowed, of course, to simplify your circuits if, of course, it's not changing what you're looking at. To be clear, let's move to like this 0.2 circuits where I only have the source E1 on. You can see that these two are in series, and like associating them is not going to change the current flowing through them. So you can clearly get straightforward I stars E1 equals to E1 over 2R. Same for I3 actually, except that it's going to be a minus this time. So again, combining these two R won't change the current here. They are both in series. So if now I move with the two arrows here, the sign is going to be negative. So I star E3, so this was E1, equals to minus E3 over 2R. And then, well, pretty simple. Here you have, let me finish this real quick. So you have I0 flowing here. You enter in a node, so you can deduce the value of the voltage here. Sorry, the current here. So it's I0 minus I star I0. Then I move to labeling voltages. And you end up by saying that this voltages here equals to this voltages there, because they are both linked by the same node here. Okay, so you end up by saying that R I stars I0 equals to R time I0 minus I star I0. And then you got your I star I0 value, which is going to be 2R I0 divided by R. So you get I star I0 equals to I0 over 2, and you're done. So I star equals to the sum of this guy plus this guy plus this guy. This is how the superposition theorem could be used. Instead of starting from the beginning with the original circuit, which looks complex, if you start applying the mesh law, etc., spreading everything, then it might be difficult for you because you may again have a system of equation, blah, 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 blah. But if you use here the superposition theorem, then you face simple circuits, quite easy to handle, and you reach the final result super easily. Okay? Do you have questions on this superposition theorem concept?
So, I mean, we just add them afterwards.
Exactly.
Okay, yeah, no, it's clear. Thank you.
Okay. One thing you really have to pay attention at is like keeping the same direction of, do not forget the or lose the information. If I stars is in this direction, then all the I you're gonna looking at are in the same direction. If not, of course, you won't be able to sum them directly. You have to play with signs, which is not good because it's a source of mistakes. So just be careful of that. So if you have no question and if the superposition theorem is crystal clear for you, then please try to apply it in the circuit we just made. So we move back to this circuit. You have two.
Excuse me.
Yeah.
I just wanted to say that I have to go because we have a lesson in 20 minutes.
Okay.
Thank you and happy
pleasure.
holidays.
Yeah, you too. Enjoy your break.
Thank you. Bye.
Bye. So this is our resistor. So the idea is to redraw each time for the two cases. One, in the first case, you just leave the source E on and turn the I0 off, redraw the circuits and look for the current flowing through R. So here you're looking for IE. Here you're looking for I0, and then you will mix both to get IE plus I0, and you should end up with the same result that we found previously. It's your turn now to work and try to solve this circuit. So in this specific example, using the superposition theorem is maybe not the best option, because is it really simplifying the circuits by solving a simpler circuit? Not really sure. But again, this is just for you a way to practice it, and maybe you might face other circuit where the superposition theorem is the best option. So I leave you with this. Try to practice this for the last minutes we have. You already have the result of the current we are looking at. I'm gonna write it down again. Just as a reminder.
In this case, is it? But I mean, we still use well, all the other methods. We're going to see, do they all use the node?
No. From now, we have seen only superposition theorem. You know that the superposition theorem is using Kirchhoff law, and that's the only things you have to use.
Okay.
Yeah, next time we will see the other Tevna and Norton methods, and next time, each time we will see another method. And at the end, once we will see all these methods, just a small point on power, and we have done with the program of electrokinetic one. Then it's going to be only practicing.
Excuse me, I have a question.
Oui. Sorry. Yes.
It's about when you explain the superposition.
Sorry, I can't hear you well.
It's about when you explain the superposition theorem.
Yeah.
There was a circuit where you wrote, where the number 3.
Yeah.
You wrote that 2R I star I0 is equal to R I star minus I star 0, and I don't understand why.
In fact, you applied the mesh law in so you agree with my labeling in this circuit number 3. Okay, circuit number 3. You have the labeling of the two voltage on both sides. It's UR1, let's call it here, and UR2. Okay, and because the terminal of these two resistors are linked, in fact, well, UR1 equals to UR2. And even if you don't see that, you can apply the mesh law on the surrounding mesh, and you get also the result UR1 equals to UR2.
But why is it a 0 in front of the first R?
So then, because I'm doing my express computation maybe too fast. So then you agree because UR1 equals to R time I star I0, okay? And the other one equals to R I0 minus I0, sorry, I0 stars, like this. Is it okay?
Yes, okay, we see.
Okay, then I move this guy here. So I have 2 R0, 2 time R time I0. This is not more. Then I simplify by R, and I end up with I star I0 equals to I0 over 2. Okay?
Yes, thank you so much.
Perfect. And we are done with today's session. If you have questions, again, feel free to drop me an email, use the forum on Moodle or anything else, whatever methods you want to use. I wish you a good break. I know the conditions are not far from being perfect, but hope you will have some rest Enjoy a bit. I hope your family, and we will meet on January in good shape. And yeah, Merry Christmas, Happy New Year, and see you next year. Bye bye.
Thank you. See you next year.
Thank you, you too.